So today, first up, we have a talk titled Quantum Computing, What, Why and How by Dr. Amlan Mukherjee. Dr. Amlan Mukherjee is an experienced researcher in the field of optical semiconductors, optical electronics and RF integrated circuit design. He graduated from the Tata Institute of Fundamental Research and spent more than 6 years in Germany as a postdoctorate fellow at the University of Paderborn and University of Stuttgart, where he also mentored doctoral students. He then joined QpiAI, initially as an advisor, but now as a director of quantum hardware and research. QpiAI is a AI, ML, and quantum model generating platform as a service PaaS company backed by the most advanced computing technology. QpiAI innovation is advancing basic pillars of human progress, including Industry 4.0, life sciences, finance, transport, and space exploration by simplifying AI and quantum. Dr. Amlan Mukherjee also has 12 publications, a patent in the field of quantum dots, and is an expert with semiconductor nanostructures. It's my pleasure to invite Dr. Mukherjee today. Sir, the screen is yours.
Thank you, Praveen. Thank you for such a kind introduction, and thank you for this opportunity to present, kind of represent here QpiAI. However, I must confess this talk would be of a general kind and mostly targeted towards undergrads, and it will be a popular science talk rather than a technical talk here. So I see a lot of expert in the audience. So I first, please excuse me in that regard. Yeah, so let me begin by presenting my screen. Am I audible, right?
Oh, yes, sir, you're audible.
Yes, okay. Then I share my screen. I believe my screen is now shared. Can you see my screen?
Oh, yes, sir.
Okay, thank you. Yeah. So quantum computing, there's a lot of hype around this subject right now. There's also a gold rush. So this would be, again, as I say, a popular science talk on what, why, and how about quantum computing. So, but first of all, we have just heard about QpiAI. I am from QpiAI, from the quantum hardware division. So QpiAI is one of the first Indian startup that is attempting to build a quantum computer so based on silicon, essentially. So one part is, of course, an integrated software stack to run the quantum computer. On the other hand, we'll have something called an optimizer chip, then a classical control chip, and a quantum processor, all integrated at different temperatures. We'll understand why as we go on in the talk. So this is a classical and quantum hybrid architecture. I'm going to talk about a little more about this at the end of this talk. But for now, the agenda is what is quantum, why go quantum, who is going quantum, and how to go quantum. So that is today's talk. So it's divided into two parts, as you see already. So the how part is a bit longer. I mean, they're equal parts now. So let's begin. So of course, why quantum? Because we live in a quantum world. For example, atoms, molecules, sun, transistors, everything that you see around yourself is actually working on quantum principles. Here is an example of hydrogen wave function. We see there are dark regions. In the bright regions, there are electrons. In the dark regions, there's no electron. So this phenomena is due to quantum mechanics. And similarly, as you grow up from atoms to molecules to solid state systems such as ice over here, one needs quantum mechanics to explain all this thing. And therefore, as you know, one of our favorite scientist, Nobel laureate Richard Feynman said, nature isn't classical, damn it. And if you want to make it a simulation of nature, you better make it quantum mechanical. So we really need quantum computers to simulate nature. So with that essence, we go ahead and, for example, one of the direct application one can immediately think of is simulating, a complex antibiotic and predicting its properties. For that, we really need a quantum computing machine, because an antibiotic is ultimately a molecule, and that is basically a quantum is a quantum entity. So if you want to simulate it, you need quantum computers. So that is one of the motivation. So what is a quantum computer and how it is different from a classical computer? So in a classical computer, in that sense, you have bits 0 and 1. while in a quantum computer, you have qubits. So in a classical computer, the bit can be either 0 or 1. We all know it. But in a quantum computer, they can be in a superposition of 0 and 1, and therefore they are called qubits. So what that means is essentially it can be both 0 and 1 at the same time. And you have to do something called measurement to actually determine and find out the probability to have it in one state or other, to repeatedly do it. So I will try to explain this in a tangible way later on. So why quantum computer? So quantum computer has these three superpowers. It has many, but one of the most important part is quantum superposition, quantum entanglement, and quantum interference. So these are actually used for, you can think of like parallel computing. It will boost in help in parallel computing. It can help in finding correlation in systems, and then amplify your results in the quantum interference. So these are just words right now. So I'd like to explain it, trying to make it a bit intuitive. But in that way, I will trade for accuracy and precision with ease of understanding. So let's start with superposition. So a classical bit, for example, can be in 0 and 1. That we all know. And a qubit can be in a superposition. But what is this superposition? So the idea here was first, put forward, but more clearly by Schrödinger's, and this is Schrödinger's cat example over here. So imagine there is a cat that is inside a box, and the box is filled with a poison which is triggered by an alpha particle. Now, emission of alpha particle from a nucleus is a probabilistic and is a quantum in nature, in a sense that you really don't know when the alpha particle has emitted. So if you don't look at it, so everything is inside the box, so you don't know when the alpha particle is emitting. When the alpha particle is emitted, the poison box is broken by hammer, and the cat dies immediately. Now the interesting point, if I ask the question, is the cat alive or dead? Then we are in a confused state, because we don't know. We don't know the alpha particle has emitted or not. We don't know the poison vessel has broken or not. We don't know that the cat is dead or alive. So in that case, we say that the cat is in superposition of dead and alive. So this is the kind of notion that one has to understand. I understand here it is not so intuitive, and that is the nature of quantum mechanics. So, but it can be used to solve real life problems. And one of the things one can immediately understand that this can be later on used for parallel computing, because you say dead and alive at the both time. Okay, another non-intuitive or really bizarre phenomena in quantum mechanics is entanglement. Again, I'm going to try to explain a bit, but however, this is not the right explanation, and this is not, there is no classical analog to explain. So one can imagine that if you have a red ball, or red color, or a blue color, if you mix them, you get something called magenta. But we all know magenta really doesn't exist. If I have zoomed in that part with a camera and took a photograph of the screen, actually you see that the screen is actually consists of red pixels and blue pixels. So magenta actually never exists in nature. This is just a kind of superposition that one can imagine of red and blue, but it doesn't exist. Okay, now imagine that we have two particles, and this two particle has a property of this color. Let's say the one particle is red, the other particle is blue. We make them come closer such that they interact so strongly they become one entity, and that is what we are showing here as this magenta bar. Now suppose by some magic or some way you just separate them very slowly without disturbing them, quantum mechanically. You don't disturb or you don't measure what they are. So you separate them, they're still behaving as if there are two balls, but they're pink, because they have just interacted with each other and they have quite strongly interacted. Now, if I want to ask what is really the color of this ball, then one has to really look hard. Once you look hard, when you really try to measure quantum mechanics, then this ball will either turn blue or red, because magenta never exists in nature. It cannot be magenta. So if it is blue, the other ball would be red, because they were previously like that. On the other hand, if it is red now, the other ball has become blue. So we see there's a correlation that is happening over here. And that is one of the intuition that one can develop for entanglement. However, once again, this is an analog. This is just for understanding. This is not the reality. There's no classical analog to explain entanglement. Taking these two phenomena and interference, we can think about that this has a quantum advantage. For example, you can prepare systems in superposition. You can do evolution of such system and ultimately get to results, or which can be measured ultimately. Again, to give you just one example, probably again, this is not quantum mechanical example. This is just a simple example to understand what kind of parallelism we are talking about. Suppose I want to find out a needle in a haystack. So one can go on with a looking glass and keep on looking onto the haystack, where is the needle. But this is a time consuming and it's a lot of effort to put in, and the result might not be satisfactory. You might not even find the needle in the haystack. On the other hand, if you take the entire system, which I would like to call a superposition, into water, immediately all the hay will just be floating on the water and the needle will sink down at the bottom. So this is a kind of, one can think of, this is like a powerful parallel computing that is going on, right? All the water is acting parallelly both on all the hay and the needle at the same time. This is something we also do in quantum computing. So such inherently parallel computing is really useful. And for example, optimization, finance, drug discovery, there are plenty of examples that they could be used. However, these algorithms are being developed even now as I speak. So one of the interesting thing is that you could also do something like an selective amplification here. What do you do with that? So for example, in this example, if I put a magnet below the water, then if it is an iron needle, then it will be attracted even faster and will sink even faster down, and all the hay will be still up. So this is one of the idea that this is how things actually can be worked out. That's the parallel computing in quantum. Okay. So once again, I was saying all the time trying to motivate about different quantum problems that could be solved. So of course, in the shorter term, one can do energy efficiency optimization, logistics, cross industry cybersecurity, and even with higher and higher qubits, you could do finance and portfolio optimization, risk minimization, drug discovery. And while the other hand, well, these will expected to take longer. While in the very short term, one can do actually efficient AI processes, material science, and some model discovery using machine learning. So there are AI models that have. So now there's the next thing in AI that what one could do is actually discover models. So you give your data and then you want to discover which model fits your data the best. Instead of you selecting the data and try to fit in and optimize the model, you give the data and try to find out the model. So this kind of model discovery, quantum can also help in quantum computing. So again, molecular discovery, there are plenty of, this is small snapshot. This is a motivation slide. So we are currently over here. Why don't you see all this thing actually? Because the capacity is we are low. Right now, the classical computing itself is much better than quantum. We need really an exponential jump in the number of qubits, which is happening, as I say. But one day it will be so that we'll have an opportunity here, which will beat the classical systems, and then we'll have the quantum advantage. We'll come to that later on once again. Yeah, and why quantum now? We have been saying about all this thing about quantum, but why quantum now? Because we are getting to the limits of classical computation. If you take the example of transistors, they're getting narrower and narrower. After some time, they will be tunneling through. They will not work. And as we speak, any kind of heavier and heavier computation really needs a lot of energy, power. And if you find clever ways to get around this, probably you could actually get, at least in some subset of some problems, that you can get quantum advantage where you can beat classical system given the fact that you have enough number of qubits. So again, what examples? Artificial intelligence, machine learning, optimization, material, in basically pharmaceuticals and cybersecurity are very near term, and the expected total available market is approximately $65 billion by 2030, as estimated by IronQ. This is a company. Okay, who is going quantum? Who is actually investing in quantum? So basically everyone. So if I look from US, it's 1.2 billion. So to Germany, 3.1 billion. The entire European flagship is 1.1 billion. China is a big player in quantum, is investing around, estimated again, as 10 billion. India is also investing about 10 billion. These are all government funded programs that I'm talking about. Apart from that, there are private initiatives that have been taken. So that is there. So basically everyone is interested in quantum. Everybody is investing in quantum. Quantum is really hot. Yes, once again, again an advertisement. The quantum market is expected to blow up by, say, a compounded annual growth rate of 56%, and expected to reach a $65 billion by 2030, as estimated by IronQ. This is a quantum computing company. So now coming to the second part, and perhaps a bit more interesting part, is how to build a quantum computer. So building a quantum computer, we already have divisions and criteria. It has to be scalable, well-characterized qubits. We have to initialize them. They should have long coherence time. Universal quantum gates, measurement and readout should be efficient. So all this thing ultimately means that we need a really good system. And at least the minimum requirement for such system is to, like a proof of principle is, two-level system, you need superposition, you need to show entanglement. That is it. And of course, there are practical requirements, easy for integration, long coherence time, scalability is an issue, high fidelity, low latency. And of course, what is really the elephant in the room is that we need high temperature operation. That would be the best thing to go after. So that is there. So what are those ultimately qubits? I'm talking about qubits a lot. So here is the qubit zoo. I have not included NV centers here, but let's say all the major ones are included. So we have on the other one hand, solid state system, for example, superconducting, spin, topological systems. These are all solid state systems, but the point there is they have to be cooled to temperatures like 20 milli around that they work around this temperature. On the other hand, we have other flavors of qubits, like an ion trap, when the ion is itself is a qubit, or you have cold atoms or neutral atoms that can be used as qubits. Apart from that, you have integrated photonic circuits that can be used as qubits. So these systems are not exactly solid state in the sense that apart from the photonic part, these things are actually in high vacuum. They do operate at room temperature, but the associated optics, let's say, or optical detectors, most of the time goes to cryogenic single photon detectors, or ultimately will rely on some kind of cryogenics later on or very soon. Even for ion traps or everything, one has to think about switching them quite fast, and that would require cryogenic electronics. And that is one of the interesting things. But on the other hand, I will be more talking about solid state as I go on. But one of the interesting things that I want to put at this point is all of this system has one thing in basic, that they are basically reducible to two-level system, that you have your 0 and 1, just like your classical switch. However, this is quantum, and then you have a quantum control or gating of the system. You can measure the system, you can initialize the system. So this is what is common about all the systems. So the major challenges of all entirely building of all this quantum computing devices is that you need to scale the number of qubits. You get advantage only when you scale, when you really go towards 1,000 qubits, towards at least 500 qubits. Each day, this number is being pushed by classical computing, and it's going higher and higher. So we really need a large number of qubits. We need preferentially millions, probably. Yeah, and we need to do precision control and gating of such systems. That is the challenge that everybody is facing, everybody is trying to solve. Yeah. So, okay, to keep them cool, we need cryostats. So one of the really indispensable tool in such solid state quantum systems is a cryostat. For example, this is a dilution refrigerator. The lowest stage is actually colder than the universe. So this is like 20 millikelvin. It's really cold. And one of the issues right now that people are facing, if I go to the next slide, is, for example, this from D-Wave, is the wires that is connected to actually communicate with the qubits here. The qubits are at the last stage. They're at 20 millik. These are superconducting qubits from Google. So as you can imagine, as you want to scale up higher and higher, the number of wires would be larger and larger. And such a large number of wires can actually lead to heating load on this system, on this cryo cooler. On top of that, it could be extremely difficult to actually scale beyond a point. You cannot have so many wires. So one needs cryoelectronics as an essential part of such quantum computing devices. So that is one of the problems that QpiAI aims to solve in very near future. So how do they look like? Well, this is like back to the past, in fact. It's like the EDSAC, or the electronic delay storage automatic calculator, something like 1940s, is to take racks, and racks are a full room for a simple calculator. And today's reality is something around that. They are almost the same. We need a whole full room of electronics and a huge machine to run a few quantum calculation. So right now they look like that, but one has to understand, look, we have come a long way from 1940s. We have already like 80 years from now. So think about it. If we have 50 years from now, we'll have really nice quantum computers, maybe even before that. So just imagine, maybe that time one would have a quantum computing wristwatch. I don't know, maybe. So once again, so next I'm going to talk more about semiconducting solid state systems. So once again, why semiconductor qubits here? Because so recently we've seen the coherence time has been improving quite exponentially. There is an increase of fidelity, but the most there's a potential for the scaling up. But the most interesting part over here is that these semiconductor qubits could be fabricated using already available fabrication labs or foundries all over the world. So that compatibility with CMOS processes is the advantage. So I show here the general architecture here about a semiconductor qubit. So this is a bit involved here, but let's say it was a very general one. This is nothing very complicated over here. So what you have here, these red puddles that you see, are actually confined electrons, single electrons, by the way. The single electrons are controlled by these gates. So these green and orange gates are what controlling the confinement potential around it. And then, then you can trap a single electron. And what you can then do is apply a magnetic field. What will this do? This will Zeeman split the energy levels of an electron, and it will make sure that it gets to either one spin or the other due to the temperature itself. You could do some initialization trick with it, and then you could use another wire, this red one, with an alternative magnetic field to flip the spin. So this is your quantum system I'm talking about. You're flipping your spin from 0 to 1, or spin up to spin down. So, and this structure, this unit could be repeated multiple times, and then you could have a quantum computing device in semiconductor. That is one of the approaches that has been taken. People are working on it. There are many ways to detect it. One of the way to detect it is to have a very narrow tunnel junction kind of a very narrow path for which a single electron can pass. Depending on the presence of this electron over the current is affected in this kind of narrow channels. This is how you detect presence of an electron or absence of an electron. It can also be spin dependent. So that could be also worked out. But this is a very general sketch. This is not how exactly it looks like. What we are trying to do is a similar thing. However, don't go by this cartoon. The whole point of this architecture is that you want to implement that using conventional CMOS devices. This is where QpiAI comes in. So QpiAI is a company which is exclusively working on, let's say, cryogenic electronics and making scalable qubit integration using CMOS devices. So we really based on normal silicon CMOS technology, really made in foundry, and we want to exactly put architecture like that, however, inside or compatible with a transistor. So you can think about these gates would be from a transistor. Okay, so going ahead, so this would be the quantum processor. You would need the quantum control chip, which will control this qubits using these gates that I already talked about here. So these gates actually are controlled by this another chip, which is the quantum control chip. And also this quantum control chip will also supply this alternative magnetic field. This external magnetic field, however, will be supplied by an external magnet. And everything, all this thing will sit at 20 milliK, while the control chip will sit at 4 Kelvin. And on top of that, there will be a classical optimizer chip that will be full with AI and some quantum inspired hardware that will sit at room temperature, and that will control the classical control chip. That is the entire stack from the hardware side, which is a hybrid quantum classical architecture. On the other hand, we'll have, of course, the software stack that has also should be scalable, and this should be like talking to really CMOS silicon quantum dots at the lower end, and while on the top end we will have a software which is quite intuitive to program. By the way, the software is now available for 15-day trial. This doesn't include the lower part, but it has a simulator inside it. You can find it on our website. Yeah, so this is a software stack that is being developed, and that would be integrated with this kind of quantum computer, and hopefully in, let's say, in very near future, one could demonstrate at least a few qubit quantum computing device, and from then on, one can scale it to make it a practical quantum computing device. So that is it till now. Okay, where it will be useful, once again putting much emphasis on the use cases: supply chain optimization, route optimization, resource allocation, job scheduling. Essentially, where any kind of optimization, where classical methods are not yet giving the right or close to optimal results within energy efficient ways, quantum can be applied. Similarly, one can do something like threat forecasting. Again, these are all quantum machine learning, and so there are different flavors that it can make out of quantum. So right now there is really a huge emphasis, at least I'm not from the software side, but the software people tell me there's a huge emphasis right now is to actually build these algorithms which are compatible with also hybrid algorithms like with AI and quantum machine learning to do a lot of things that were not possible purely classically, or let's say, or also purely quantum. We already know that we don't have much quantum power. Okay, going ahead, again, apart from optimization, we'll have some kind of disease diagnosis, which is now a hot thing right now, or drug design, or even right now, a few years ago, we have heard about protein folding from this AI, I forgot the name, from DeepMind, protein folding has been, has been demonstrated, protein folding solution of protein folding, but this could be even enhanced using quantum simulation. That is the general understanding. Apart from that, there is also, there's a lot of application in finance. This is really a hot thing right now. People are asking for this kind of computation machine, so that they could do, lot of portfolio management, risk analysis, fraud detection. So there's a lot of applications that are waiting for such machines. So the takeaway is, this is hot field. Only thing is that we need to deliver. There is an hype. Okay. Once again, this is an advertisement for my company. So I have put a comparison with all the leading quantum computing companies over here. So one flavor is superconducting, one is photonic, one is ion trap. So the major problem with all of these companies is that they have perhaps very good qubits, and but there is some problem or the other. For example, superconducting qubit, the size of the qubit is typically of the range of 1 micron or so. So if you think about a billion qubit, maybe you have to pack it in a clever way, but just the back of the envelope calculation will give us, this is like a huge, large machine we are talking about. Also, the temperature of operation is 10 millikelvin or 20 millikelvin. If we have a billion qubit or million qubit, probably with all the wires or some way or the other, if you have so much area to be covered, you need a huge, even a nuclear power plant perhaps, to actually cool down the systems. And these cooling systems are being built now. For example, IBM have come up with a huge cryostat, but inside in which an entire human being, two human can stand together, a huge cooling machine. So that is there. On the other hand, photonics do work at room temperature, but one hides under the carpet is that the lasers and the superconducting single photon detectors that they use has to be at low temperature. Also, later on, the fast operation, if you want to do really fast operation, then one really need cryoelectronics, because cryoelectronics gives you faster and more good control, high fidelity when you do to control such quantum systems. Ion traps, on the other hand, of course, have large, vacuum chambers. Probably it could be shrinked in. People are working on it, but again, you need lasers, optical detectors. They are not quite integrated systems that one can think of in a small package. Maybe they will, but in future. But for QpiAI, there is an advantage that we have. We work on standard in the CMOS device, so manufacturing techniques used by industry to perhaps make these quantum computers more compact. Probably a desktop size quantum computer is possible in the near future. Maybe 1K, and maybe 5 years, 10 years from now, who knows? We'll have a room temperature quantum computing device using semiconductors. Maybe. Right now, one can think about what we have right now with the universal quantum optimizer as a chip at room temperature, and the quantum computing device could bring us already to an edge where we can take the advantage of bits of quantum computing power and the best of classical computing, and give us some edge in at least some of the applications that I have already presented. And with that, okay, sorry, references are in form of links. This I have to change. If you want, I can give you later on. And I'd like to conclude over here that quantum computers are not something in the future. They are here right now. We are all poised for a quantum revolution that can come anytime. However, there are various design challenges in terms of qubit design, integration that definitely exist. One has to really make those strides and discoveries and inventions to really make a powerful universal quantum computer and make this quantum dream come true. Yeah. Thank you very much. This is me. This is my email ID. This is the company website. We are quantum computing startup, as I've already told you. So what is very interesting is today we are launching already joint certification program on AI and quantum. This is a 6 months certification program that you can do this is in joint collaboration with QpiAI and CEE, Center for Continuing Education, IISc Bangalore. It's a 6 months program starting from today. You can enroll now. First batch is unfortunately already full, so the next batch is probably will start from 1st of July. And that so next batch enrollment for the next batch is open. So today we already start this course. This is already online from today onwards. And once again, thank you, and I'm open for questions. Maybe yeah.
Thank you, sir, for that wonderful talk. We should take any questions from the audience right now.
Yeah. So how do I get to know the questions? Sorry for this. I didn't actually. So how do I get the questions?
So if there's any questions, I'll read them out.
Okay.
Hello?
Yes.
Yes, go ahead.
Praveen, I think they are raising their hands. You can ask them to unmute.
Yes. Shivashankar Maniyam, can you go ahead, ask a question? Hello, Shivashankar. Your hand is raised. You may ask a question. Okay, it doesn't seem to be responding. Shubhranshu Sharkar, you can go ahead and ask a question. You can unmute yourself and ask.
Hello, I just had one question. You mentioned the typical size of a qubit. How is it determined, the typical size of a qubit?
Yeah, good question. Maybe I can go back to my presentation. Yeah, so what I meant there is actually a physical size. So let's take this example, for example. Yeah, so this, for example, can you see the superconducting circuit over here? So this entire circuit is probably around a millimeter or so. These or a bit maybe a bit smaller, but these wiggly things are inductors, and the qubits are actually small there. So I say, when I say qubit, I wanted to essentially impress upon the fact that the entire system is required here, and that is of the order of a micron or so. Could be compacted a bit more, but that's the order. That's not nanometers like for example, a transistor is really like 22 nanometer, 7 nanometer, even 5 or 3 nanometer transistors are coming up. So that is the qubit size I'm talking about. For example, here you have a gate-defined quantum dots. You see the bar over here is 500 nanometers. So this is still large for what we have here. But one can go even smaller in such cases. So that I meant by exactly size of a qubit, the physical dimension that is required to essentially realize a qubit. Sometimes it is not so clear there, photonics or other things. Yeah.
So the reason I asked this question is, so when you mean qubit, you mean the junction as well as all the connectors?
Yes, as well as everything, because that's what matters. You could have multiple junctions, but ultimately it is entirely the system we are talking about. So I take into account the other peripherals that is required.
So now, do you think it's impossible to fabricate a Josephson junction in the same geometry, or is it just not there because of the things that we talked about, that the CMOS technology is just not advanced like superconductor. I mean, CMOS technology is more advanced than superconducting circuits.
Yeah. So
But is
Josephson.
there a technical?
No.
Yes,
So yeah. So Josephson junctions are definitely be possible. You can make smaller Josephson junction as you want, and they're really small. The junction itself is quite thin, but that's not the point, right? Josephson junction is just not a qubit. You have to entirely make a qubit out of it. It's just one part of it. One has to understand this in LC circuit ultimately. So your LC circuit has a junction and as an inductor and that nonlinear inductor, and then that makes it not harmonic. That is one of the tricks one as plays, especially with trimon. So these kind of qubits, but as you say now, this is getting a bit complicated, right? It's just not a single unit that you're going to replicate. You have to replicate the entire LC circuit again and again. And if you think of million to billion, then that becomes a problem. But for right now, as you say yes, this qubits are the best in its class right now in terms of scalability right now. For transistors, one has to really, so there has been already been shown as we speak, they're getting better and better every day to actually, but there is a problem there also, in a sense that you need to really have some design rules broken to actually realize this architecture that I talked about. So we are working to get around that, and in very near future, probably we can work with foundries to break those design rules, and then what we can make is a nano wire with a lot of gates on it, and that would be a perfect system to exactly make a quantum computing device, yeah, for semiconductors. Yeah.
Okay. Thank you.
Thank you.
Thank you for the question. You may lower your hand now. Mr. Melvin Varghese, you may go ahead with the question.
Thank you, sir, for your wonderful talk. So my question is that at this point, we have many cloud computing facilities like IBM Qiskit. Okay, so
yeah.
if I'm giving a smaller circuit, are every circuit's result really from a quantum computer, or is it just stimulated version, the result? And my second question is about you focused about the cryogenic part of the hardware. What about the pressure in the computer? I mean, the hardware we are talking about. I just wanted to ask the second question because recently we found a resulting super conductivity at 15 degrees Celsius. Thank you, sir.
Yeah. Thanks for the question. Okay, yes. So when you run a small circuit on an IBM, Qiskit kind of a thing, this goes inside a simulator that is sitting probably on a laptop or somewhere in the cloud also. But later on, if you really want to access, a proper quantum computer, it is also possible to, I believe, to 16 qubits or something around that number. It is still possible. I don't know exactly the charges. Probably some lower, even maybe 4 or 8 qubits are also free. I don't know. So this is there from IBM. Next speaker is from IBM, and you can of course ask him. What we are trying to do here is really don't go by that route. So yeah, so our software already has a simulator inside, and apart from that, one day it will be connected to really real life quantum computing device that is also there. So stay tuned, please visit our website. And regarding the second question, pressure, I didn't understand that very clearly, but I think you are indicating that one could actually achieve superconducting devices and even near room temperature. Is that the question?
Yes, sir. The recent advance in superconducting, is that a good green signal for our research?
No. So the recent advances is about high pressure superconductivity, right? This is about room temperature superconductivity, a bit with the pressures around the center of the Earth. So if you put pressure like center of the Earth, you will get such superconductivity. So the next step would be to have just saying junction, then a circuit out of it. Can you imagine about it? It's not possible. So right now at the room temperature one, like with this kind of material that we talked, that has been shown to do superconductivity, right now it's not possible. However, there's nothing like impossible in this world. Maybe in very near future one could invent or discover a superconductor that works at ambient pressure and temperature, and then on that would be one of the very interesting phenomena, and probably it will have even larger impact than just quantum computing. Of course, one should be able to make quantum computing advantages out of it, when trying to implement a quantum computer out of it. But there could be even more impact if we discover such an or invent such a material. That is also there, yeah. But for now, the particular material you cannot make a qubit out of it.
Thank you, Doctor. We have a few more questions from the chat. So, Mr. Mohsen Ilahi asks the following question. Are there any other parameters you talked about that can be more precisely quantified to quantify that the quality of the qubits? I mean, do you have all parameters that can pinpoint which type of qubits are best for development of the most efficient quantum computer? Basically, they're asking are there other parameters which quantify the efficiency of computing?
Yes. So there are now different parameters one can think of. So one of the most important parameter that I briefly brushed, I already just talked about it a little bit. So decoherence is one of the important parameter. If you have a strong decoherence, then your quantum computing device is not so good. So basically, you need decoherence. This is a system that you switch it on and it remains on for how much time. If you make a quantum superposition, the quantum state survives for how long? That is the decoherence we're talking about. So that has to be there. So then there are, if you want to say more precise, I don't know of more precise stuff right now. Even the simple parameters that it is required to make quantum computers are being tested, and the limits of each of these systems are being tested every day, and try to make better out of it. The best out of what we have as qubits. However, recently, I think 2 years or 3 years back, IBM have come out with a measure called quantum volume, where they wanted to say the more important parameter is a quantum volume rather than just qubits. So that is another parameter that people actually use to quantify quantum computers. But all these are, again, very much in an experimental and in a way quite not established. Yeah. Any other question?
Yes, sir. Next question is by Mr. Sanjeev from BioCost Life Sciences. His question is, are there any products released or near release by QpiAI using quantum computers? And which area does QpiAI focus to release their first product, and when?
Mm-hmm. Okay, by the way, QpiAI is just not quantum, it's also AI. So its AI products are already selling. We already sell our AI products, and that's how we earn money while we do research on quantum computing. And of course, the first thing we have already launched is a Qpi Explorer. This is software that can be used for educational purposes. That I just wanted to show you that we have this certification course. It includes this software I'm talking about. So this software, there is a software called Qpi Explorer. When you enroll for this course, you get this software free for 1 year. So that is one of the first quantum products out in the market. The next thing we want to build is, of course, the quantum control chip. So that is already being designed as I speak. So that would be a low temperature cryogenic circuit that could control qubits, almost like, it's a bit general. You could control semiconductor and say superconducting qubits there. That is there. You can control with this, and you could also, yeah. So of course we are also working on, I see somewhere, quantum error codes in the next question. Yeah. So that's of course a dream. We were parallelly working on quantum error correction. We're trying to file patents right now. We have already filed patents on certain quantum correcting architecture. We are on the hardware side, so we deal with the hardware of it. And then which area here QpiAI is focused on the first product. And yeah, the first product would be already released. Is this educational software that you can use at your home? You can simulate quantum circuits, and later on you can add on, even now you can add on GPUs, and later on you can have live quantum computing, real life quantum computer integrated with the software to run some programs. That is there. So that's the next thing. And next product would be a quantum control chip. And finally, in another 2 years, you will have a quantum processor. Of course, we are working on the back end for the quantum processors. Hopefully, in 2 to 3 years, one could have at least a simple quantum processor. And then to 4 to 5 years, one could have even more powerful and probably a commercially usable, viable quantum processor. Yeah. And all the elements can be used for digital. Yeah. Okay. I'm just reading for the next question. All the elements can be used for and digital machines. Only silicon germanium can be used. Please explain. Okay. So yeah, silicon and germanium are really the workhorses in terms of semiconductors, especially for transistors and devices. This is mainly due to the fact they can be very easily or nicely doped. It is nothing to do with other things. Of course, there are other materials like gallium nitride, gallium arsenides. They're of course costly. They're not single. They're compound. They have to make it properly. It's of course research. There are certain areas where they get advantages. But why silicon and germanium, or rather silicon, is ubiquitous is that it has very nice solubility, and you can dope such materials very easily and with a wide range. So you can make CMOS device, you can make BJT, you can make a lot of other devices very easily. In a sense, easy in a sense that a lot of things dissolve. For phosphorus dissolves quite well, boron dissolves quite well. Almost any material, silicon will just grab it and put it inside, and that would create a doping. And then you had a P and so one of the interesting questions that I had in my life sometime, in fact, somebody else asked somebody else this question, an expert. What is a semiconductor? That person was an expert, and he answered that if you can dope a material, if you can dope an insulator, such that you can make a p-n junction out of it, then you can call it a semiconductor instead of an insulator. So here we have a fine example. Silicon is of course an insulator at T equal to 0. Let's say at absolute 0 Kelvin, it's an insulator. It has a band gap, but you can dope it very nicely to make P and N, E and N regions. You can make a P-N junction. You can make a PNP. You can PIN, NIPI. You can do whatever you want. So that is because of its solubility. And there are other factors, of course. I'm just stating one of the super thing about silicon. So that is why they are found in every digital machines. And that's thanks for this question. And anything else? Yeah.
No, that's all, sir. I think that's all we have for questions. Dr. Amlan Mukherjee, on behalf of IEEE-IISc Communications Society, I request you to kindly accept this plaque as a token of our appreciation for taking out the time of your busy schedule to deliver such an informative talk.
Yeah. Thank you. Thanks a lot.